Hello everyone, and welcome to another webinar co-organized by the ANT Neuro Education. My name is Frank Zano. I'm the founder of ANT Neuro, and I act here today as the moderator of this session. At ANT, we regularly host webinars with leading neuroscientists. Today's event is certainly a highlight in this series, and it's my great pleasure to announce Dr. Sebastian Olbrich to you. Dr. Olbrich is co-founder of DeepPsy, a company that offers treatment personalization based on the individual biological profile of patients, and Deputy Chief of the Center of Social Psychiatry at the Psychiatric Hospital at the University of Zurich in Switzerland. Sebastian is one of the leading European experts on deep learning applied to EEG and mental health. He will shed light today on the topic Brain Learns Brain, EEG and Deep Learning Methods. Dr. Sebastian Olbrich earned his MD degree at the Ludwig Maximilian University of Munich in Germany. He will start very soon a new position as Chief of the Center of Affective Disorders in August, actually. Moreover, Sebastian has also been the president of the International Pharmaco-EEG Society since 2018. Sebastian, thank you so much for accepting our invitation and being with us here today. I'm very jealous of the great name you picked for your company. DeepPsy reminds me of Deep Purple, my favorite rock band, roughly 200 years back in time. The stage is yours. Thanks.
Thank you, Frank, for the nice introduction. Yes, Deep Purple is a nice association, and however, it's deep. And so today we're going to take a look at deep learning and the EEG, just as you said. So to give you a small teaser in the beginning, let me start the slides. Yes, you know that there's a lot in the media about deep learning, promises and the calamities of deep learning. Some say we have to fear that, some say we have a bright future using artificial intelligence. However, everyone has to make his mind, but what is sure is that we can use the deep learning and the artificial intelligences for analysis purposes in the future. So this is what this talk is about, and to give you just a short overview on where especially deep learning is hidden in is, for example, the Google AlphaGo. This was this deep learning machine that learned to play the very complex game Go better than humans within a couple of days, and it learned best when it played against itself. So the machine learned by the machine. If you want to try after this session some very specific and deep learning websites, try this. It's called This Person Does Not Exist, and it shows you every time you hit the enter button a new face that doesn't exist, that's generated by convolutional networks. And this is another pretty example of learning by deep learning. Is how old do I look? That's me. It was not quite right, but still pretty close. So try it out. Last but not least, you all have your smartphones, and you know you have this face recognition, and we know there are lots of ethical issues. However, it is impressive what convolutional networks performing deep learning are able to do. And most impressive maybe, and just a little bit in the future, the autonomous driving, where we have the sensors, and the plus to what these other techniques I showed you is that this is online proceeded and calculated data streams. So that means this is live and not offline. One last example, which is quite impressive, and you can try that out or have a look at it. It's called DALL-E, and here you can give a sentence to the machine. The machine understands the sentence and generates a picture following your sentence. Just an example, an armchair in the shape of an avocado, and you see the pictures. They're all generated by the machine and can do thousands of these pictures. So what is the difference between artificial intelligence, machine learning, deep learning? I know you all start from different levels. For many of you, it might not be a new thing. However, I will just mention that deep learning is some kind of subdivision of machine learning. Machine learning is a set of tools that allow to analyze lots of data, learn by data. The more data you have, the better. And deep learning is some kind of special because it reproduces in a way the brain calculates and proceeds information, and this is where we are at the moment, and this is where the title for this webinar comes from. The brain learns brain. We are trying to understand the brain in neurosciences, And we are using deep neural networks now to understand the brain. And our brain, again, has to integrate these findings. So by a way, we had a dilemma in Germany. It's called Baron Münchhausen. And this was a guy who tried to push himself out of muddy water by taking his own hair and lifting him out of the mud. So this is some kind of what we are trying to understand what human consciousness, what human cognition and so on is by using the same machine. So however, you can say this is a dilemma or a paradoxon, but we still try, and I think it's good that we try. So let's have a closer look at what is deep learning in comparison to machine learning. When you do machine learning, you say you want to classify a rocket or a car. And what you have to do first is you have to find features of that labels. For example, a rocket has an engine and has a spike, or a car has wheels and glasses. And then after you have features, you apply your algorithms, and then you get classification for new examples, rocket yes or no, following your features. And this is exactly the step, but deep learning just jumps over. It gaps this bridge. You don't need to define features beforehand. Deep learning learns its own features. So it mines the whole data and finds the features that differentiate the best. You just have to provide the right labels and tell him and give him large enough data sets. Then the deep learning machines will learn to classify, if there is a signal on the data, of course. So what is behind these deep networks? And the main, or the core, the heart of it is the convolutional networks, the convolutional layers. And this is some kind of architecture, as I said, that resample the visual cortex and how it works. The main thing is that it's some kind of follows the Herbst rule, and I will show you in just a few slides later. And there are others that contributed. And there was this so-called AI sleep within the past century, but this was over until Schmidhuber provided his first papers, and Hinton had his great papers, and Jan LeCun, you see it on the right side, had his great papers, all on layers, all on forwarding information, all on networks. So let's have a look from the biological side, and I promise this is the only biological slide you're going to see. And the Herbst rule, it says that if you have a constant information exchange between neurons, that this exchange leads to an increase of the strength between the neurons. That means you fire together, you wire together, the connection gets closer. And this is some kind of what the deep learning nets do. We change the networks, the weights of the nets, by presenting new data and having the classification. So in a way, we follow Herbst rule. And here are the two core elements. So this is the convolution, and we're going to have a look at that. And then we have the pooling. I will get to that later. So let's have a look at the filters. The filters you have to understand is the main part. The filters mean that is some kind of the features, but you don't have to find them. You give some kind of random matrices as filters. And a filter is a feature that might be in the data. So you see a filter on the right side of the left pane, and you see the input. And what you do is you go through all the input data, for example, the EEG or the picture with faces, and try to find if there are features that are in the filter. Okay, and on the right, you see the new output data that shows how likely it is that that feature is in that area that you just scanned. So in a way, you see that from another point of view. You scan through the whole data and generate a new matrix that contains the information, if the information was in the data or not. Okay, so now gets to the next point, and this is just important. So you see you have some condensing of information. It converges toward a point. And then we have the pooling, and that is some other kind of convergence. Because you see on the left side, this is the input data. And by pooling, you decide for different pooling sizes to put together some matrices. And as you see by the color, the highest number is a 6, and this just is forwarded. Or the 8 for the upper right matrix is forwarded. So you are condensing the information, following the filtering with your expected features. So you might ask, okay, I can imagine when having a face and then looking for shapes and curves and eyes and so on. Well, how can I do that with the EEG? Okay, what is an EEG by means of a picture? And the answer is the EEG is can be seen as an array. Here you have a single trace of an EEG, maybe O1, and this is an array. And you can have many arrays in a multi-channel EEG, and all of you may have a multi-channel EEG these days. And if you put them in a matrix, then you see, well, it's a little bit similar to a picture because it's a 2D array. It's a 2D matrix. So if you look at that, you can generate some kind of 3D landscape out of such a matrix. And if you go one step further, then you see that out of this 3D landscape, you can generate a picture. But we now have is some kind of picture, okay? And the good thing is that now you can use the EEG array of a segment, as you see, in 10 seconds or 2 seconds or 1 second, as some kind of a picture. And that means you can use all of these great and famous AlexNet and whatsoever competition winners that were used for image classification. You can use them for EEG too, because EEG essentially can be seen as a picture, okay? And this is pretty great. However, sounds nice, but does it work? Does it really work? And well, this was the question we asked ourselves with Michael van Putten and Martin Arns a couple of years ago during the IPEG meeting, International Pharmaco-EEG Society meeting. And we asked ourselves, if it really works, we really have to test it for some kind of ground truth. That means not some kind of paradigm that we are not sure if it really exists, what we are measuring, so some really valid ground truth scenario. And let's see if the label can be learned by the deep architecture. And what you see here is Konrad Zuse, one of the first inventors of computers, and Marie Curie. You all know her. And you see an EEG of a male and a female. It's not the EEGs of them, it's just them for symboling males and females. However, no human, at least no human I know, is capable of classifying male or female, but just by looking at the EEG. However, what we did is we trained 1,000 EEG data sets, or trained a network, as you can see here, with I think it was 9 layers, or we'll see later. Trained it with 1,000 samples, and then we gave it a new 300 data sets to classify, is it male or is it female? And just by looking at the 1,000 EEGs, the network learned how to classify into males and females with an accuracy of almost 84%. So that was a proof for us that a machine can extract features from the EEG and make labels and classify. So here you see the used network. Convolutional networks, different. You have the dropout function, of course, to prevent overfitting, as you know. And in the end, you have dense layer where it all gets together with a softmax algorithm to make the classification. So this is, in fact, the most basic implementation that you can use. So what hardware software did we use? I mean, you can use Linux or Windows systems, maybe even you can use Mac systems, but Linux might be best. And what is really important, you need to use NVIDIA graphic processing units, because other graphic processing units are not capable of handling those large data sets. And you have to use Python. MATLAB is not as far as Python is at the moment by concerns of deep learning. I recommend using TensorFlow backend and Keras. So the wrapper is Keras and the backend is TensorFlow. You can also use CNTK from Microsoft or Tiano. However, those are similar or equal. We use TensorFlow and Keras backend. What's very important, use a normalization of your data and apply the early stopping also to prevent overfitting when using different models. And in the end, and this is very nice, I wish I knew of that before, use Google Colab. Google Colab, you can use GPU units for free, and you can upload your Python code, you can program there. Everything is, you just need a Google account and you can just start straight with deep learning. So this is pretty cool. Let's get back to array preparation. Okay, since this is a webinar and I try to keep it a little bit hands-on, online. So what do you have to do? You have the different epochs as you see. An epoch is, for example, 1 second, or as we used, 2-second segment of multi-channel EEG. And you have, of course, different epochs of one subject. Maybe you have 100 seconds, so you have 52-second segments, 50 pages, as I call them, and all those 50 pages are one subject. Then you have to put them together, the different subjects, but don't mix the pages of the books. Okay, it's the same in your bookshelf. You don't mix the pages of the books. Don't do that. Okay, and this is because of you have to stack all the different labeled subjects in the end for your master matrix to be provided, and you have to randomize them into a test set and a training set. And the most important thing is for group-wise analysis that you have to keep the different subjects either in the testing or in the training sample. Don't mix it. The EEG has a very intra-subject homogeneity, but it's very heterogeneous between subjects. So if you have the same subject within the different samples, the deep learning net will know the person that this EEG is from. It won't learn the label, but it will know, well, this is, for example, Adam, and Adam was male. I remember that was Adam, so this EEG must be male too. So please be very careful by splitting that up and keeping subjects separated. Okay, once again, split it. It is another case if you want to do some kind of learn the representation of an EEG or have lots of data of one subject and want to define, as we will see in the end, is he doing this or is he doing that? Then of course you cannot split inter-subject wise, but have to do that by condition wise. So what happens in such a deep network? As you can see here, and these are the image classification, you see the different layers now, okay? The different layers of filters. And the bottom, this is the most basic layer. You see features like lines or circles or something like that. Then we go a little bit higher in the middle. You see more complex shapes. For example, on the left, you see like a nose or maybe it's some kind of eyes. And just in the end, you see the representations in the filters, the faces, okay? So the higher you get in this hierarchy, the more complex things will be. And we will see later, or we see now, what we have done in the EEG, and this is the gender net classifying males and females. This is our picture, okay, made gray, black and gray. So 256 data points, 1 second, and the channels stacked on each other. And as you see, if you go through the lines, you see here is an overview, the different layers. It's upside down, so the highest layer is the most basic layer, and you see it's just some kind of random noise. It's very basic features of the EEG. It's just spikes, so to say. Later layers, it's layer 3 now. You see they get a little bit information. You see some kind of information. This is 2 seconds, so you see some kind of alpha or beta rhythm there. And if you see at the FFT as provided on the right side, you see it's around 20 hertz. And if you then go to the last layers, you see those spike or those trains occurring only during several channels or at certain occasions. And then you have some kind of spatial resolution if you want. So you see also the EEG net learns features of the EEG for classifying. And as you've seen, the beta activities seem to be most important. We looked at the conventional analysis and there was no significance when testing using conventional analysis, but there was, if you looked at the picture, of course, a difference in the activity. However, not significant, but the deep network learned it by using this feature to differentiate between males and females. And very nice, there was a replication by using more conventional analysis, but having the knowledge that they have to look at the beta frequency. And the Bukova group from also Martin Brunowski and Jiří Horacic in Prague, they were able to replicate that. Very nice, where you can see brain learned brain. We tried to differentiate, use deep learning, extracted features, and applied them again. However, this was several years ago. Nowadays, there are more advanced techniques to get to know what the machine learned. And as you can see here, it's a picture from Van Gogh, and this is what the deep learning makes. It tries to associate things that are not there, and this is how it learns things, okay? And so this is what we did. Just to give you an overview over the next sample, we had this gender net differentiating males and females, and then we applied that to a data set of homosexual males and heterosexual males and tried to differentiate, and it was able to learn that. And the nice thing is that it was some kind of transfer learning. We used the same net, differentiating gender, and now differentiating the sexual orientation by a way. So this is very interesting. You can use the basic features of EEG for different questions. However, what I want to go through is we now use that data set to exactly look at what features of the EEG we were looking. And this is a method called GradCam method. It's gradient class activation mapping. And you see a picture of 2 elephants, and you see this was a picture classification where the deep network looked at. It looked at the not at the grass, but looked at the teeth and at the ears of the elephant to know, well, oh, it's an elephant. And we can do the same for the EEG after we trained that. So how did the network learn this is a homosexual male or a heterosexual male? And here you see the different layers. I don't know if you can see in the background there is this EEG curve of 1 second or 2 seconds, sorry, and the different filters. In the beginning, very heterogeneous kind of noise going there, and the coarser the filters get, the more clear is where the machine was looking at. And in the end, you can average all that, of course. And here we see an example of a 2-second segment. And by looking at the bottom right, you see there the red color. That means this was the most important feature of the EEG. And we see the very pronounced alpha activity, very steep alpha activity at occipital and parietal cortices. And this was the main classification feature of that segment. And this is very interesting. And if you then average that over the whole course of time, maybe 100 segments of one subject, and then apply a source localization technique as we did, you can find out which region of the brain was responsible for the activity that made us differentiate between the two groups. So what I want to say is you can use deep learning to differentiate groups, and then you can learn back what made it differentiate. And this is very cool. Okay, and maybe we can have the first poll. So I see.
Very good. So I can read it out loud. So Jens, here's the first question. Do you have experience with deep learning analysis for EEG? Please select yes or no.
How can I see the results now?
You see the results. So the majority votes for no. It's 21% saying yes, we have experience with deep learning analysis in EEG.
Okay, very interesting. Thank you. So I think this is the picture as we see now. We just made, and we will see the later a review, and we were a little bit surprised how little papers were out there on EEG and deep learning. In other fields of medicine, it's much more advanced, but we still think that this is some kind of a new area where you can use deep learning and associated techniques. So I want to, if you get what it means, try it, use it, collaborate maybe with data scientists. But nowadays, it's not that complicated. You can use it and learn it by yourself, especially using such things as Google Colab, for example. Okay. So thanks for the first poll. And now we get to the clinical usage. As you have heard, I'm a psychiatrist. I'm interested in prediction. So we have a data set of 300 subjects at high risk for psychosis. And we wanted to know, can we differentiate between subjects that can or stay without a psychosis after 3 years and some convert to what is psychosis within 3 years. And here we see, again, it was possible to differentiate by giving a new test set. And what I want to make the first point is the highest sampling rate had the highest classification accuracies. And also by looking at here on top, you see the less you manipulate the data with a high-low pass, you get the better results. And also the more or less the higher layers you use, the better results you get. So that means in the end, and I don't want to make the content of that analysis don't want to announce it too much, but it tells us that we will use, we need large data, maybe we need unprocessed data, and we need large networks, and we need high sampling rates. And I will to get that point later. However, why did I show you some clinical data? And this is what I want to make the point also, although it's a deep learning webinar. We are in the year 2021. If you go to a doctor and you broke your leg or you broke your arm, you're going to do some objective information retrieving. He's gonna do an CT or an X-ray or whatsoever. However, in the same year, if you go to a psychiatrist, it's still about, well, let's talk for half an hour and maybe we should take that pill, maybe you should take psychotherapy. There's no objective information, and this is what we want to change, what I want to change as a psychiatrist. And I believe that techniques that like deep learning applied to EEG will be able to extract information out of those brain waves that we need to address the right treatment in psychiatry. However, here are the results from our first review of EEG applied to clinical EEG data in psychiatry, and we found 33 studies. The problems were the same as in other EEG studies. We had small sample size, no replication, fast validation, we see that it's a powerful tool, but still it's a long way in the clinic. What maybe is interesting if you are thinking of applying deep learning to EEG data is what input should be the data be. And I provided you information about the raw data, the time domain data, and I think this it's worth a try, of course. Others apply FFT data, frequency data, or spatial data by providing the array where the channels are, also connectivity data. So you can play around and you can change the input space. I think the most information is in the time data. However, you can use different input forms. So the lessons learned from that study I want to share with you is, as I said before, but this is the most important thing you have to remember: separate the training and test data set. And this is also what puts deep learning and machine learning above the conventional statistics. We have separated tests and training sets, and this makes it very strong. If you have findings, it might be very strong. For labeling groups of subjects, always separate subject-wise. Only use the test set for a limited set of trials and keep it unseen for model selection. That means don't play around with the models and then present again the same test set. You have to keep your test set in the close set. And only in the end of all your switching and tuning has been done, you can apply your test set. Use data augmentation strategies. We know that from the field of image processing that they switch or turn the data, they make jitters and so on, and we have to do that in EEG research too, so that we don't need that much EEG data, but can produce larger data sets with augmentation. Enrich the data with spatial information, with information from the clinics on gender whatsoever. Enrich the information. Describe your samples very carefully. We know that you can introduce bias by using deep learning networks. That's because of the black box. If you only present I don't know, very large persons to your network, it learns that large persons, maybe, I don't know, all live in Germany. But this is not true. It depends on the sample that you present. So be very careful what sample you present and describe your sample when you publish. Test different deep learning hyperparameters, as I just showed you, and try transfer learning. So that was the point about deep learning as what we have done. And I want to stress one more point, and that's that. When I was a little bit younger, it was last century, we learned that sampling rate matters, but over 512, it doesn't matter too much. Maybe if you're doing fMRI, you need higher sampling rate to get rid of the artifacts. But otherwise, everything above 50 or 60 hertz is muscle or noise, and we mustn't record that. And I learned that to get to know something from a single segment, such as in ERPs, you have to average. And nowadays, using deep learning and using high sampling rates, I say maybe we are wrong. And why I say that, I just want to give you a small example. We did a small study, and it's in preparation, where subjects had to think on 5 different entities, and they're very different, like number 2, summer, tiger, right hand, pain. So totally different words with totally different concepts behind it. They had to lay there, and the words were presented by a voice randomly, and the subject had to imagine, for example, something like summer. And if he was realizing or she was realizing, wait, I cannot imagine summer anymore, he pressed a button and a new word was presented. So it was some kind of resting state, and the words changed when the subject realized he wasn't able to see the word anymore. Then we applied a deep learning classifier, intra-subject wise, of course. We have to say that we used a very high sampling rate, the 8,000 hertz with the EEG Go system that we maybe going to see later. It's also able or capable of recording 16,000, and we did that too later. We segmented everything into the imagination parts, and we had several hours of recording in 3 individuals. So this was very exhausting for one individual because we needed lots of data for deep learning from one subject. And then, and this is very special, we cut the EEG into 50 millisecond segments. But that still means, for 8,000 hertz, 400 data points per channel, for 64 channels. So just a quite large matrix for deep learning. And there was no time lock. And this is the results, and you see we have accuracy around 1/3. That is not too overwhelming, but it's far beyond random. If you apply the same machine, deep learning machine, that learned for one subject, apply it to the other, it doesn't classify anything, okay? It's very important. So the machine, the deep learning machine, was able of differentiation of cortical information by 50 millisecond segments. That's just one gamma wave, nothing more. And that means it only could be able to classify which what the subject was thinking about by looking at those 400 data points sampled by a very high sampling rate. Further, it's very interesting that this was no stimulus log, but there was some continuous information in the EEG that we were able to differentiate between the different words. So we conclude that the information is hidden between the high sampling rate data points. And just to have a look, but I just learned before the presentation that we will have a similar demo presentation before. You see 10-second sampling rate, 10 second, 1 second, 100 millisecond, and you see, oh no, doesn't look very good. But still 50 milliseconds resting state. This is what we use. There's almost no information, you think, but if you look closer and amplify the amplitude, you see that there is information, as you can see. And you also see that within this high sampling rate, the decrease or decline of the wave is coded somehow. So if there's no change, nothing happens. But if there's a change, the high sampling rate is capable of classifying that. Here you see the comparison to a low sampling rate, which is the red array, and you see the shape, the broad shape is the same. However, there seems to be much more information. And now if you apply a high pass filter, and we did that, we high pass filtered 80 Hertz, and still the machine was able of differentiating between summer, pain, and so on. And here you see what kind of information is there. It's some tooth-shaped information, but still it is an information that is in the signal. If you zoom in, this is some kind of illustration of what is left of the information, and the blue line is the 256 sampling rate, and the red line is the 8000 Hertz sampling rate, and you see there is more information. However, I do not announce that there are frequencies or neural frequencies at several thousand Hertz that we assess. No, but we assess the shape of the oscillations. An oscillation, as you see it in the EEG, is not a very biological oscillation as we know it from bridges or from whatsoever. It's just what we see, and it looks like an oscillation, but the shapes are totally different. And this is what we get with a high sampling rate. We get the shapes of the different oscillations, not only the frequencies and powers. So this is what I say. Why throw away information that we can get? We know deep learning depends on data and depends on information. So if you can apply the highest sampling rate you can get and use that information, you can downsample later any time. That's no problem. But if you can get high sampling rates, especially for deep learning, just do that.